we can start.
Yes. Good afternoon and good day to all the attendants to this seminar who occurs on Easter Friday. So we very much appreciate your participation, and we are very grateful to Professor Beste Basciftci for her intervention, for her contribution today. So I very briefly introduce her work. She's, as you can see from she's assistant professor in the Department of Business Analytics at the University of Iowa. And she had her PhD at Georgia Tech a few years ago. And she actually was, she comes from Istanbul, and she attended and she had a master in industrial engineering from Bogazici University, where she also graduated. So her scientific interests are rich, and she works on stochastic mixed integer programming and distribution robust optimization. And very interestingly, she emphasized the game theoretical elements in this area of stochastic optimization. So finally, I would say that she's very interested in applications, particularly in supply chain management, energy, and sustainability problems. And she received several very relevant awards during her short career. So we are very pleased to have her here, and I would like to welcome you. And then we have, as usual, 45 minutes time for presentation, and then sometimes for questions and remarks. Thanks a lot, Beste.
Thank you so much for the kind invitation and also for the kind introduction. I'm really happy to be part of the Stochastic Programming Society seminar series. And in today's talk, I will be talking about some partially adaptive stochastic programming approach. So if we think about sequential decision-making problems under uncertainty, so we want to achieve, in general, full flexibility. By full flexibility, what I mean is, say, if like once kind of uncertainty is revealed over time, then we would like to dynamically also adjust our decisions as uncertainty reveals. However, in some business contexts, like the companies or in some problem settings, they might not be able to work in a fully kind of agile way or flexible way in which they can revise their actions in each time period, and they might need some commitments in that setting. And if we think about some example problems in that domain, some setting can be in supply chain management, in economics, or in policy making. And in supply chain management, if we think about the production-related decisions, sometimes the producers or manufacturers might not have the flexibility to frequently adjust their production quantities or their schedules because of some contractual restrictions or because of high setup costs. And sometimes also they might need some of these, as I said, contractual restrictions to different customers or different settings. So because of that, some level of commitment can be desirable in their decision-making problems. Another setting can be in policy making, like once, say, those policymakers would like to, say, design a policy where some people can kind of select whether they would like to use that policy or not. And in that setting, also, what we can see is like those decision makers, like if they provide a fully flexible solution, by meaning that, like, say, those policies can be adjusted over time, then in fact, like the ones that will be kind of using those policies might not prefer them, and they might also desire some level of commitment or some level of a certain level of like decisions in their problem, a certain level of static decisions in their problems. So because of these like certain contexts, we can think of some problem settings where we want to limit the number of revisions to a previously made decisions, or if we think about like in a multi-stage setting, we want to commit decisions at certain times. So our goal is to essentially find the right balance between decision flexibility and commitment for such problem settings. And then if we think about this one's relationship with stochastic programming, so first of all, like the most kind of suitable approach for multi-stage or multi-period decision-making problems is multi-stage stochastic programming, where we have full flexibility in our actions. and we can revise our decisions accordingly. And on the other hand, if we think of two-stage stochastic programming for multi-period decision-making problems, we have some static decisions, which also we refer as sometimes here and now decisions, where we need to commit them ahead of the planning for the remainder of the planning horizon. So we can think of them two stages, some kind of an approach with some level of commitment, because we commit those actions ahead of the planning. However, what if we have some problem settings where we do not want to be that kind of static, and we do not want to be also that flexible, which is somewhere in between two-stage and multi-stage stochastic programming. So in that setting, what we want to propose is to find an optimal balance between decision flexibility and commitment by kind of optimal determining the best states to revise decisions for each variable with limited flexibility. And we do them at the beginning of the planning to determine our revisions time throughout the planning horizon. And we try to label this approach as partial adaptive multi-stage stochastic programming approach. So let us see what we mean by this approach more formally within stochastic programming context. But before that, in fact, I would like to also just motivate the idea of this concept of revision times. And for this one, we can think of Nussbander problem as an example setting, which is like one of the most studied problems in the literature. And in this setting, let us consider a multi-period Nussbander problem. And we are only given like one revision time. And the goal is to kind of determine the order amounts in each period while minimizing the total expected cost. And in this setting, we have some random and independently distributed demands, and also we are given some unit ordering costs, holding costs, and backorder costs. And in this setting, what we can do is we can just derive a closed form, kind of order of the policy, which can help us to determine how to make these ordering decisions in this planning period. And in this setting, this T star corresponds to our revision time. So by this way, we can just construct how to design this revision policy, and we will be comparing it against two kind of approaches. So in one approach that we will have in here, so this figure is just kind of illustrating that. So the adaptive one is what we have over here with single revision time, say this T star time. However, the black one here is a static case where for this 5-period problem, we commit our ordering policies ahead of the planning. So we can see its cost in this case, and this cost is a single line, so it does not change based on the revision time, because since we do not have a revision. And same applies for the dynamic case, where in this setting, as kind of information reveals over time, we have the flexibility to adjust our ordering policy at each time period. So if it is the case, which is this dynamic one over here, we have the least cost as we expected because of this additional layer of flexibility. And if we have this kind of adaptive approach under given revision times, what we can see is the objective value is somewhere between this fully flexible or this dynamic approach and the static approach. And what we can see this in fact was something we kind of see, and before we in fact try this. But the other thing that we can see here is that depending on when we revise our decisions, objective value changes. So this kind of motivates us to optimize the time of revision, because it significantly impacts our objective function value, our cost, under these settings with limited flexibilities. So in this talk, like once we have this motivation from this Nussbander problem setting, our goal is to propose this formulation for the generic setting. So in the previous case, we had single revision time for a Nussbander, but now we will be proposing like a generic problem formulation, and we will provide some properties to improve the computational efficiency of the formulation, because as we will be seeing shortly, it will be a large-scale problem. And then we will go back to our single revision time setting, and we will provide some kind of results for specific structured problems. And then for the generic problem, we will be providing some cutting plane-based solution approach. Once we also have like mixed integer variables in this problem settings. And finally, we will provide two sets of experiments, like on two different problem settings on lot sizing and generation expansion planning, to see the value of this approach and its computational tractability. So first of all, now like if we go back to the stochastic programming and scenario trees, so here's just kind of an illustration of what we have as a scenario tree for 4 stages and 2 branches at each node. And here like we have this node n for the node, like letter n for denoting nodes. And in terms of the decision variables, like we have 2 sets of decision variables. On one hand, we have the state variables, which we denote as with the variable xn. And for the stage variables, we denote them with the variable yn. And then like here we can see like a path from the root node to a specific node n. Then if we think about the multi-stage stochastic programming formulation, so here's like a generic formulation where we say want to minimize some cost function, and in here this constraint, we want to just couple the state variables and stage variables while carrying information from the previous stages. So here, like, which is why we have the path part in here to carry some information from the previous ones, and then we have the stage variables here. And also we can have some constraints for our state and stage variables at each node. And if we think about the 2-stage stochastic programming, so that's a variant of this formulation, what we have is, we have the same set of 2 constraints as before, but we want to enforce some static relationship for our stage decisions or for our here and now decisions, which is by enforcing this constraint that we have in 2b. And as you can see here, what we have is it will enforce our like stage variables to be the same throughout throughout all different time periods, and we need to kind of commit them ahead of the planning. And if we want to see how these decision structures relate into the in these frameworks, is that like in terms of that like 4 time period and 2-stage scenario tree. So the first one is the case of for the multi-stage where we have that full flexibility as information reveals. In the second one, we have the case for 2-stage for the state variables, for those x variables. And as you know, like as we commit them ahead of the planning, because of that non-specificity constraints that we added, we have the static relationship for those. And in the last case, we have the setting and where both stage variables are in this problem setting, we kind of allow them to be fully flexible. So which is why our y variables follow the same structure for this formulation. However, we can see the difference in terms of multi-stage and 2-stage decisions. So now let us go to the setting where we want to add some limited flexibility due to these different potential problem contexts. And in that setting, we introduce this parameter mu to be the number of times that each state variable can be revised. So it's kind of a maximum kind of amount that we have. And for a scenario tree, we define some subsets for each state variable for potential revision times. So say, for instance, for kind of variable I, this corresponds to the set of times that we can revise that decision. And in that setting, like if we see the formulation, so we kind of think of different sets of non-specificity constraints to add to our formulation to ensure this relationship. So first of all, we have one set of constraints for the point where we see the first revision time, where we label as this like TI1 star in this setting. And this is very similar to our like 2-stage formulations at the beginning. However, things become a bit kind of complicated once we look at the other revision times. So say if we look at the case after the last revision moment, then we still need to ensure this equality. But here in the right-hand side, now we need to consider more conditions. And if we think about the very last case, which is in fact the case considering to the revisions in between. So now we need to consider like a more kind of complicated set of nodes to capture that intermediate revisions in between. So now we have a formulation where we can capture this limited flexibility setting with these decision variables t star. However, here, like if you just look at this formulation, the complexity is that these t star variables are also decision variables. So we do not know when we will be revising our actions. So because of that, this formulation is not linear. It is not something that we can give to the solvers to solve the problem. So because of that, we need to just come up with some way to reformulate it such that it can be solvable to capture that dynamic revision time setting. And if we see how this structure means in decision structures, like if we connect it with multi-stage and 2-stage stochastic programming, here is some kind of illustration on several settings. So in the first figure, for instance, we say consider one state variable at a time to just to kind of illustrate, but note that in this framework, we can, like each state variable can its own set of revision times. But for this kind of illustration, we are just focusing on one state variable at a time. So here is, for instance, the case where we have like one revision of this specific variable at stage 3. So then what we can have is for the first 2 periods, like we have the static settings, then at the third period, like we kind of see the uncertainty and then revise our actions for the remainder of the planning horizon. Or say if we have the settings where we revise at stage 2 and 3. And if it is the case, then for instance, we have this action like first revision at time 2, and then the second revision at time 3. And in the last case, we can see how it changes if we have, say, the second revision at time 4. So as you can see, depending on how we revise, we have different decision structures and different ways to handle uncertainty. And if we come back to the formulation to see how we can reformulate it in a like mixed integer linear programming formulation, we introduce this variable r, which we will refer as the total number of revision points for that state variable I until stage t. So it's an integer variable. And as you can see, this variable can take at most the value mu, since we allow at most mu revisions at the planning, but it will be somewhere in between like having 0 revisions up to mu revisions in the setting. And once we have that, in fact, we can obtain the formulation where we have the same objective and same constraints for the multi-stage and multi-stage setting. However, now we have these constraints from like 4b to 4g to capture that revision parts. And now we introduce these constraints in here. And as we see, like these r variables can be at most mu, and the difference between them should be like at most 1 in the setting, since in each consecutive period we can have, between each consecutive periods, we can have at most 1 revision. And if we think about some properties or like some kind of observations over this formulation is that, so in this formulation, we can say that there exists some kind of optimal solution where this constraint is binding, meaning that like in one of the optimal solutions in this current setting, we use these mu revisions for each state variable. So this gives us the case to see that like this approach kind of explores the full flexibility as possible under the limited, under the commitment that we need to do with those at most mu revisions. And we can also make the observation that if the state variables are pure binary, then in that setting, we can relax the integrity conditions of our R variable, which helps us to speed up the computation part if we have such a structure for our problem. However, like if we just look at the formulation again like this one, it's still a very large scale formulation with many decision variables and many constraints. And if we just, for instance, think about the size, which is the case that we have over here, say, for instance, for a scenario tree with 10 stages and for, say, 2 branches, then we have like 700,000 of these non-specificity constraints that we have. And if we have, say, a case with 3 branches, then we can have like hundreds of millions of constraints to consider. And as you can think, this can lead to some memory issues or some problems that we might not be able to solve with the off-the-shelf solvers. So to kind of address that, can we improve our formulation further? It was our like next question. And in that setting, we can kind of observe some properties in a way that we can kind of at least make some 90% reduction in our constraints by kind of observing some properties, in the sense that we see some repeating patterns within the non-specificity constraints. And we had like 3 sets of reductions in our results. So the first reduction is kind of cyclic in the way that we kind of check the non-specificity constraints within a given time. And we want to kind of eliminate certain repeating patterns. And also we want to check, for each time we want to check these patterns with the patterns that we have seen before by checking the coupling constraints that we have for the previous periods. And by also doing that, we were able to reduce certain number of constraints. And also we have some certain reductions which are based on our parameter mu. And by using like some propositions that we have in the paper, we were able to obtain an improved formulation. And if we think about the scale of this improved formulation compared to our initial one, Here is just like giving some kind of comparison where the first one is the case where we just have the initial formulation. And then, for instance, if we have these in here, like we have the number of branches and a different number of stages in here. And we can see like significant reduction in the problem formulations from like millions of constraints like in here to now thousands of constraints in the setting. So it's like a significant reduction by applying these results. And if we think about this problem itself, this problem is NP-hard. So this is a hard problem that we want to solve. So even if we save these reductions and even if we have improved formulations, as we will be seeing shortly in the computation results, the problem is hard to solve. So we will need to develop some solution algorithms to handle that. And also even before that, I want to discuss a bit further about the connection of this approach with two-stage and multi-stage programming settings. And in this setting, what we can see is, so like say, this approach is essentially a generalization of two-stage and multi-stage because depending on how we select our variable mu, it can reduce to both two-stage and multi-stage formulations. Say, for instance, in here we compare the objective function values under different mu values, where recall that mu was our kind of limit on our number of revisions. And if say our mu is 0, then this essentially reduces to two-stage formulation. Or say if our mu is equal to t minus 1, then it reduces to the multi-stage formulation. And for all the approaches in between, we have this kind of relationship in terms of our objective function values, which is something that we can expect because of the additional layers of flexibility between different formulations. So now our goal is to just kind of illustrate how these results perform when we consider a specific case, which is the case when mu is equal to 1, and we can see whether we can come up with some kind of results on the value of this approach in comparison to two-stage and multi-stage stochastic programming. And we will be labeling this approach as adaptive two-stage stochastic programming approach. And then we will go back to our generic setting. And for the generic setting, we will be providing a generic cutting plane-based solution algorithm for solving these problems. So now let us start with this specific case where mu is equal to 1. So here now T star corresponds to our revision time, since like we have like now like a single revision time, and this T star is essentially a vector consisting of the revision times of each state variable. And in this setting, what we have is, which is what we have just seen over there, the multi-stage objective is the least, two-stage is the highest, and this approach that we have with single revision time should be somewhere in between. And our goal is to derive some bounds on this difference between two-stage objective function minus like multi-stage, and also the difference between two-stage objective function with this adaptive two-stage approach. And we will be referring the bound between two-stage and adaptive two-stage as the value of this adaptive two-stage approach. So here I would like to just note one thing. Although we are making comparisons against the multi-stage approach, in fact, in our problem setting, multi-stage approach is just a relaxation. So it does not provide us feasible solutions because at the beginning, we assume that we have a setting with limited flexibility. So because of that, like although we may make a comparison against multi-stage approach, we are just using as a way to kind of provide these solutions qualities and see how they perform. However, they do not provide a feasible solution for our problem setting because of our limited flexibility assumption. And for our kind of technical results, we'll be focusing on like the specific problem structure, which is capacity expansion planning problem. And in this setting, like in the left-hand side, we have this generic problem. Say in the objective, we are minimizing cost. And then we have like a constraint to couple our state and state variables. And in capacity expansion planning setting, these are generally for like demand satisfaction related constraints. And in here, this X is denoting our capacity kind of acquisition decisions, like our state variables. And Yn is our state variables, which are like given those decisions, how we can kind of allocate our capacities in this formulation. And if we just decompose this problem into like into the setting, what we can see is now like in this formulation we have Yn in here, and we now introduce this Qy problem, the sub-problem in the setting. And this sub-problem is for the case when the Y decisions are given. And we will be calling this problem as the single resource sub-problem, But also you might have noticed that this problem is also in the same format as stochastic dot sizing problem. So like although we have this specific substructure as part of the capacity expansion planning problem, the results that we will be obtaining shortly will be also valid for the lot sizing problem because it also has this structure. Once we think of, say, this left-hand side as some given parameter, like demand, for instance, if we think of this left-hand side as I said, like a demand, then in lot sizing setting, this is the problem setting that we can see in that domain as well. And here we have one important observation which really helps us to derive these results. The constraint matrix of this problem is totally unimodular. So because of that, we can benefit from duality and the linear programming relaxation of this sub-problem to obtain some kind of analytical results as we obtain bounds based on this single resource I sub-problem. So to that end, let's, if you like, just focus on the single resource sub-problem. First, let this VIM, this VRITR star, and VIT be the LP relaxation, like linear programming relaxation values of this multi-stage adaptive two-stage under the specific revision time and two-stage models. And in here, we are just, for now, considering the case where this T star is given, like under a given revision time, T star. And our goal is to obtain some bounds on these objective function values for each of these approaches. So if you think about the multi-stage setting in the literature, in fact, there's already a result for this like single resource problem to find some kind of lower and upper bounds on this objective function value. And in this setting, what we can see, so here this A corresponds to, like, if I just come back to here, in this setting, we consider both both uncertainty in our constraint and also uncertainty in our objective function, because the cost is uncertain, which is something that we can see here. And we label this left-hand side as delta. And once, like for a given delta value, we can think of this as demand for the single resource problem, for instance. And in this setting, depending on also how the demand value or this value changes, we can also obtain, or like the bounds that we will be seeing here can change. So the bounds essentially based on those two parameters that we have here. And in this setting, what we can derive is we can obtain some lower and upper bounds on this VRTI star value, like which is this kind of objective function value in terms of our revision time, cost, and demand data. And also we can show that by selecting this T star at the first time period, then essentially this reduces to two-stage stochastic programming setting. So in that setting, we can observe that our existing result reduces to this specific case for the two-stage formulation. So now the next question is, how can we benefit from these results to obtain some bounds on this, on the quality of our adaptive two-stage solutions in comparison to these approaches? And by this like previous result, what we derive is, like we want to derive a lower bound on this gain against two-stage approach. And also we want to also find a kind of an upper bound on the loss versus the multi-stage approach. So we cannot achieve the multi-stage case, but under with limited flexibility, we want to kind of minimize this loss. And also if we think about the two-stage case, we want to be more flexible than two-stage. So we want to be better as possible compared to that setting. So we want to think of these lower and upper bounds as we see the quality of the solutions and also as we design some solution algorithms for the specific problem structure. So the goal is to kind of obtain these bounds, so see the performance of this approach as a function of the revision point, because as you can see, these bounds will depend on when we select the revision point. And then we can also obtain some kind of insights based on these kind of analytical results. And in this setting, we will be focusing on two cases. For the slides, I just put the case where we have the similar like cost values, like for instance, the costs are stationary, but we can also do a similar analysis for the case when the demand is stationary and cost is changing. But for now, let us consider the case where we have some stationary cost structure over in our scenario 3. So then in that case, what we can observe is these bound reduces to like these two kind of expressions. So the first one was the bound against the two-stage approach and the other was the bound against the multi-stage approach. And in here now we have like a more nicer form of the bounds because of this stationary property, because we can reduce some of these expressions. And then what we can say is our goal is to maximize the gain of this approach in comparison to two-stage, and also minimize its loss against the multi-stage approach. So it is kind of maximizing the first term and minimizing the second term to kind of achieve that. So the goal is to find, because in here, these bounds are for a given revision time t star. So now the goal is to find the revision time ti star that minimizes this expression, which we see over here for the best bound. Because in here, like the only part in these bounds that change based on the revision time is this delta plus term, which arises in both of them. However, the other terms are kind of something given to us once we have the kind of underlying uncertainty. So now our goal is to just to analyze this term to find the best revision time for our problem setting. And what we can say is, like, under a general demand structure, then, for instance, this should be somewhere between the second period and the first period that we observe the maximum demand. So it can give us some kind of insights on when should this revision time will be for a specific problem structure once our costs are stationary. And as I said, we can obtain some similar analysis for the other cases if we consider several assumptions for the demand structure as well. And finally, what we can do is we can just extend these results to the full problem, because recall that these results are only for the case for the single resource problem, but now we want to extend it for the full capacity expansion planning problem. So in that end, we just obtain some lower bounds on the objective function values between two-stage and adaptive two-stage approach by using the values that we have kind of obtained before. And then similarly, we can obtain kind of an upper bound on the difference between adaptive two-stage and multi-stage approach, and restrict this with this value. And finally, what we can do as our last step for this capacity expansion planning problem is that we can just see, we can design some solution algorithms by using these analytical results. And in that setting, we will be just presenting some high-level some solution algorithms. So in one case, for instance, we can propose some say two-stage relaxation-based algorithm, where the goal is to leverage the bound between two-stage and adaptive two-stage approach, and the bound is just we have just obtained together. And the other is the multi-stage relaxation-based approach, where the goal is to leverage now the bound between multi-stage and adaptive two-stage to design the algorithm. And finally, we will be also proposing a setting where we have this kind of adaptive two-stage relaxation approach. And in this setting, it is not based on these bounds, but we were able to show that it provides us some kind of approximation guarantee on the solutions that we obtain for the true problem. So this part is in fact based on a prior research that we have. And if you're interested, we have this paper in archive for some time to see these structures for the case when mu is equal to 1, and seeing also these results for this specific problem structure. But now, in the remainder part of the talk, I will be going back to generic setting after we get these insights for the single revision time problem setting, to see how we can come up with a solution algorithm for that one as well. Because for the generic problem setting, for generic partial adaptive multi-stage approach, we have this generic mu, and also we can have mixed integer state variables, so it can, and we are not specifically working on a specific problem context. And in this setting, our goal is to decompose the problem into master problem and sub-problem. In the master problem, we will have the set of revision decisions. And in the sub-problem, we will be solving the problem given the revision decisions. And essentially, in fact, once the revision decisions are given, essentially the sub-problem is like a multi-stage stochastic problem, because we know where those stage times will be. And in terms of the solution procedure, we will be presenting some Bender's cuts, and also we will have some kind of modified integer L-shaped cuts. So you will be seeing shortly why I call them modified. And in the computational kind of enhancements, we had some pre-processing steps to make the algorithm faster. And also we had some cuts heuristically by solving some problems at the beginning to speed up the solution algorithm. So if we see how the master problem and sub-problem look like, So now like we are going back to our generic formulation. So in this setting, in the master problem, as you can see, we only have the set of decisions for the revision times. And in here, note that the revision time decisions are kind of integer valued decisions. And then these constraints that we have here are corresponding to boundaries cuts and integral shape cuts that we will be adding at the iterations. And also we kind of start with some kind of lower bound in our theta value. And then in the subproblem, we have this kind of multi-stage type of problem structure as before, but also we have this constraint 9D. So this 9D is in fact our kind of improved constraint. So recall that at the beginning of the presentation, I give first the initial formulation, but the initial formulation was large in scale. So we had this non-specific constraints, reductions, and we had the improved formulation. So once we have the improved formulation is in fact, we only have this like single set of non-specific constraints to capture that adaptive relation, that limited flexibility relationship between the formulation. So essentially we use that 9D as our kind of improved constraint within our subproblem. And in here we solve it for a given revision time decision variable, this R bar. And then a subproblem can be like mixed integer, we can add some kind of L-shaped cuts. And the reason that I call them modified cuts is that because in the integer L-shape, in the classical one, for the master problem, we kind of expect master problem decisions to be pure binary. So one way to, for instance, to come up with the cut can be like, since we have kind of integer decision variables R, we can like kind of reformulate them as sum of binary variables and come up with integer L-shaped cuts. But those cuts will be really weak if you think of that. Or some alternative way, since we know that the difference between those consecutive two R variables will be kind of at most 1, we can leverage that relationship into our solution framework, and we can add cuts by using the difference between those two consecutive R variables, such that those variables can take like at most the value 1. So by doing that, we add these cuts, but also our subproblem can be mixed integer. And in order to handle that, also we want to add some boundaries cuts. But the thing is, in fact, like since we have the possibility of having this mixed integer setting, these cuts will be just for the relaxed problem because we will be using duality to get the cuts. However, these will be still helpful for us to speed up the solution algorithm. And as we try different ways to kind of accelerate our solution methodology, we have tried different combinations, and at the end, we have the setting where we add boundaries cut at each iteration, and we add the integer L-shaped cuts only at subset of the iterations to speed up the solution algorithms and also not solving the mixed integer subproblem at each time and solve the linear programming relaxation. And it will help us to speed it up. And also, like for the sake of time, I did not include in here, but we were also solving some shorter problems at the beginning with like shorter time periods compared to the full planning horizon. And from those, we were kind of able to get some cuts to and kind of add them into our solution framework, which also helped the formulation, helped the solution algorithm to speed up. So finally, we can move on to our computation results and see how they perform. And in this case, we have these two generic problem settings. So one is the lot sizing and the other is the expansion planning setting. And for this case, we will be defining this metric that we call as this value of this adaptive multi-stage stochastic programming approach. And in here, we just check the difference between two-stage and what we have here as this partially adaptive multi-stage approach in our objective. And we want to see its value against the fully flexible case. So for instance, if we have the fully flexibility, if say this mu is t minus 1, then this approach is essentially multi-stage and we have 100%. So if we have the full flexibility setting, then this VMS should be 100%. However, what we will be seeing is like because of that limited flexibility, we can have reduced values for this VMS. However, despite of these constraints and these limitations, what we will be seeing shortly is optimizing revision times have certain value, and even under those limitations, we can obtain a high VMS values for these problem settings. And if we introduce the lot sizing problem, here the goal is to determine the optimal production schedules of sources to cover the demand of an item or a finite planning horizon at a minimum cost. And we consider an uncapacitated setting where demand and cost parameters are uncertain. So you can also recall our single resource hub problem as that problem structure. And in terms of the decisions, we have the state variables that those like setup variables, and we have the production inventory holding decisions for this problem context as an additional set of variables. And here is just kind of illustrating how this value metric that we just defined changes based on a different number of stages and different values of mu. So here, like if we just check, for instance, the first one, the single resource means we have like a single state variable. So we are just considering lot sizing problem for a single product. And for the multi-source, we have like 5 state variables, meaning that like we have 5 products that we consider at this problem. And for the case when this I is like for the single source problem, what we can see is, so and here each of the color corresponding to different number of stages. So say, like if we start with say the stage 5, like a problem with 5 stages, then even with a single revision time, we can observe like 80% of the this value that we can get. And once we have like 2 revision times, in fact, we reach a value which is almost like 100%, and then it kind of converts to 100%, even if we have 3 revisions, which is not the 4 revisions that we could have with the 5 state setting. And similarly, as the number of stages kind of increase, what we can see is, so like even if we have a problem setting with 10 stages, then still with say 4 or 5 stages, we can obtain really good solutions, which are like kind of almost 100% value in our computational study. And similar results kind of apply for the multi-source problem. And note that in here, we kind of have different sets of revision times for each state variable, giving us some additional layer of flexibility. And one other thing that we can kind of observe is the cost benefit of increasing the degree of flexibility on the value of this approach is diminishing as we increase mu. So like in the first one, say going from mu1 to 2, we have a higher increase in this value. But say going from mu4 to 5, this increases kind of reduces, which is what we can observe in these analyses. And here's just kind of an illustration for a problem setting like a single resource problem with 5 stages. And in this setting, for instance, what we can see is if say mu is equal to 1, so here, in fact, we kind of enumerate all possible options for a single source problem. And here is the case where these revision times can be, let's say, 2, 3, 4, 5. And these are the potential combinations for 2 revisions and 3 revision time settings. Here, we can just observe the value of optimizing the revision times. Because, for instance, if we check the first case when mu is equal to 1, if we set revision time to be 2, then this value is kind of only 7%. But if we select this 4, then we can see a value which is like 79%. And the 79% is something which can be similar to some settings that we can access for the case mu is equal to 2. And also what we can say here is that, for instance, even say we have 2 revisions, we can approach this 100% value in here, even if we have 2 revision setting. But we can also see that if we do not kind of optimize it, but just kind of select this with some other way, then also we can have much less value of this approach. So it kind of shows us also this revising decisions at these kind of optimal stages can perform better compared to settings where we do not optimize, but maybe do it even more frequently or at some random stages. And finally, here is like just another illustration of value of having multiple revision. So the first is the case where mu is equal to 1. And the other cases are for the cases where we have like higher level of flexibility we can have in that problem setting. And what we can see is for the longer planning horizons, for the setting, like as for instance, number of stages kind of increases, if we have even like mu is equal to 3 or 5, we can have some stable results. But if we have say mu is equal to 1, then in that setting, we can have less value of this approach. So if the decision maker has more flexibility, then it will be better to, as we expect, to kind of explore higher mu values in the planning. And finally, I would like to just talk about the computational performance. And in that one, I will be reporting some solution, like some results for the generation expansion planning setting. And the goal is to determine the optimal mix of generation resources to meet future electricity demand at a minimum cost. In this setting, demand and renewable generation amounts are considered as uncertain. And for the decisions, we have like state variables as generator expansion decisions. And in the stage 1, we have the production related decisions. And here is just like a computational comparison of these approaches. So the first one is the first formulation that we have with all of the all of our constraints that we have. The second one, like the plus version, is the case where we have improved the constraints, where we had significant reductions. And the solution algorithm is just decomposing that problem, as we discussed with master and sub problem, by leveraging that improved formulation. And we can see step by step the value of each of these approaches. So first of all, if you look at this gap, like the first set of columns, what we can see is after some point, we run into memory issues because as you expect, we have too many constraints to take into account. So we do something to improve our formulation. And if you look at the second one, we can observe that now we have much better solutions. And if we also think about the case with the solution algorithm, we have also much like speed up in here. And in this setting, we report also this value of multi-stage in here because essentially in the solution algorithm, we add some cut heuristically. But even though we add these heuristic cuts, what we have observed is in kind of all of these instances, it turned out to be giving us the true optimal solution, even though we add those cuts at the beginning, but also those cuts are added in a way that it leverages some information from the problem itself by solving like a smaller problems as a pre-processing step ahead of the planning. And like if we just compare two kind of approach without the solution algorithm, we can see kind of up to 19% runtime kind of speed. And also on a kind of average, we can observe like 59% improvement. And also if we make solution algorithms performance against the kind of improved formulation, we can also see runtime improvements, which can be kind of up to 94%. So overall, if we combine this talk in general, in this talk, the goal was to kind of come up with some partially adaptive multi-stage stochastic programming approach to decide some optimal times to revise our decisions. And we discussed some ways to kind of improve the computational efficiency of our formulation by reducing some of our non-speculative constraints. And then also we provide some kind of analytical results and managerial insights for the case when mu is equal to 1, which we label as adaptive two-stage stochastic programming approach, which is based on this prior paper that I have shared before. And for the generic problem setting, we have this cutting plane-based solution approach, and which can be also kind of applicable if we have mixed integer variables as well. And at the end, we have these two sets of computational experiments to see the value of this approach, both from the practical standpoint and also from the computational standpoint. And if you're interested, in fact, this paper is available online in archive, so you can check it out and see the details of these results. And thank you so much for your time and attention, and also being here for this day.
Thank you, Beste, and it is extremely interesting. And so